Good morning, everyone. It is our great pleasure to host Duygu Ceylan today. So currently, Duygu is a senior research scientist at Adobe Research. She obtained her PhD degree from EPFL, where she worked with Pauli. Duygu and I are both METU graduates. She graduated from Computer Engineering Department of METU in 2007 and got her master's degree in Computer Science Department at Bilkent University. Her research interests include machine learning techniques to infer and analyze 3D information from images and videos, focusing specifically on humans. And today she will talk about 3D perception for creativity assistance. Thank you, Duygu.
Yeah, thank you so much for the introduction and thank you for having me today. So today I will be talking about some of my research in the context of 3D perception. So specifically, my research focuses on inferring 3D information from 2D content, which could be images, videos, or sketches. And I'm particularly interested in using this 3D information to understand about humans. For example, here we see a person who is standing, our physical spaces. So here we have a scene with a table, some chairs, and some cupboards, and how humans interact with each other and the physical environments. For example, this person is sitting on the chair. So why is this 3D understanding useful? Well, we are living in an era where digital workflows are becoming a part of both our professional and personal lives. If we have a good understanding of the 3D scenes, the 3D physical world, I think it has two main benefits. First, it helps us to build more intuitive 3D workflows. Let's say you want to create a 3D object or edit it or customize it. You want to build interfaces that are easy and don't require you to deal with low-level 3D information. And second of all, with 3D information, we can actually improve our 2D workflows as well. For example, we can add some 3D aware capabilities that will be otherwise very difficult to achieve. So while the goal is to use the 3D information to support these two types of applications, in my research, I'm particularly interested in answering some specific questions. First of all, of course, there are many ways to represent 3D information. So one of the first questions to answer is what type of 3D representations are suitable for a specific application. Second of all, since the goal is to acquire the 3D information from 2D content, which is itself a challenging task, one usually needs to use some priors to make this task more tractable. So the second question is what type of priors can we explore? And again, this is mostly an application-specific question. Different priors can be suitable for different applications. And finally, our observations are usually monocular content, sometimes just single images. So these observations are limited. There are many occlusions between scenes and people and also self-occlusion. So we also have to come up with methods to reason about these occlusions and see through them. So with these questions in mind, before going into some details of research work, I would like to first walk you through some demos we built at Adobe, and then let's see how we try to answer each of these questions for the different applications. So the first example I would like to show is in the context of 3D modeling. So let's say you have a mug and you want to produce a catalog image. You already found some 3D mug that you like, but you want to customize it. Maybe you want to make it a little bit taller, and you might want to change the position of the handle so that it's more suitable for your use case. So what we did here was to build an intuitive 3D editing system. The focus was more on man-made objects. So that's why in terms of representation, we actually made use of these 3D feature curves because they are the characteristics that tell you about the unique features of a man-made object. And also, in order to make sure once the user edits one part, the other parts of the mock are updated accordingly, we made use of priors such as symmetries, planarity, or orthogonality to propagate these edits. And these priors are very suitable for these type of man-made objects. Another application we built was monocular view human body motion capture, and then use it to basically animate 2D or 3D puppets. So here you see an example video. The user can select the person of interest, and then we can capture their motion sequence and then apply this motion sequence to a 2.5D puppet in this case. So in order to represent human motions, of course, skeletons are a natural choice of representation because it gives us the configuration of the different body joints. Since we are doing this task from a single monocular video, as I mentioned before, this is very subject to occlusions. Even if it is not from the scene, there can be self-occlusions. So we are, in this case, utilizing human motion priors. In other words, learn the space of the plausible human motions to complete basically the missing information and see through occlusions. Another application related to this is actually just looking at single poses. So let's say you have a huge image database such as Adobe Stock, and you want to search for some images where a human has a specific posture. And sometimes keyword may not be easy to describe the pose you are interested in. So we developed this demo where you can search based on the human pose itself. So similar to the previous application, skeleton is our representation. And this is a single image case. So we replace the motion priors with pose priors. So we make use of the space of plausible human poses, basically to complete the missing information that is very common in just single image cases. And the final application I would like to show is more in the context of 3D aware editing of images. So in this case, editing faces. So here, starting from a single image, we infer the 3D shape of the face and use this information to change the head pose. So our representation in this case is a 3D deformable model, because for human faces and human bodies, there are good ways to come up with robust deformable models. And in terms of priors, we can make use of some statistical priors about the shape of human faces so that we can infer this 3D information in a more robust and accurate way. So after seeing these motivating applications, coming back to my research, as I said, I've been mostly looking into problems where the goal is to understand humans from images, our physical spaces, and also the interaction between the two. So today I will be talking about two works in detail, one in the context of garments and one in the context of single view reconstruction of 3D objects. So yeah, let's start with the first work, where the goal was to build intuitive systems for garment design. Before going into details of what we built, I would like to first introduce you what a traditional garment design workflow looks like. So usually the designer starts with some initial sketch, which we can also call as the concept sketch. And this sketch basically gives you the idea of what the final garment should look like once it's draped on a person. Given this sketch, then the designer needs to adjust the parameters of the different garment patterns. So these are 2D patterns, and they might have different parameters based on the garment type. And then the designer also needs to drape these patterns in 3D and see if the draped garment actually looks like the sketch we started with. And as you can imagine, this is actually a very iterative process. So the designer has to go back and forth between adjusting the parameters of the patterns and then draping it in 3D. So our goal was, can we now, using some machine learning approaches, automate this iterative process? So what we want to build is a system where we start with some initial input sketch and then automatically infer the parameters of the garment. So it could be the parameters of the patterns in itself, and also how the garment would look like once it's draped in 3D. Given these predictions, then the user can either make edits to the patterns themselves directly by changing their parameters, or can go back to the sketch and make some changes to the sketch by maybe adding some new fold lines. With these updates, the system will also update its predictions, and the designer can go back and forth between these different design spaces. And once he is happy with the current design, he can also apply different textures. Since we have the 3D garment and the corresponding 2D patterns, we know the correspondence between the texture space and 3D. So it's very easy to apply different texture patterns. And in the final stage, maybe a final physical simulation of the garment can be performed to see the very accurate look of the garment. Another property of a good design system is actually retargeting. So let's say I designed this garment for a particular body shape, and now I want to retarget it to a different body shape while preserving its look. So if we can also automate this retargeting process, it's very useful. So how can we build such a system? What we did in this work was to basically make use of machine learning and large-scale data sets. So the first observation is looking at the whole design workflow. There are actually multiple design spaces the user has to operate across. First, there is the sketch space where you basically sketch what the final garment should look like. Second, there is the parameter space, which consists of the parameters of the individual patterns, maybe their material properties, and also the underlying body parameters, the body shape parameters. And the third space is in 3D, so it basically consists of how the garment actually drapes in 3D. So if we want to build an automatic system that can go back and forth between these different design spaces, we need to train machine learning models that can go from one space to the other. So that's what we did. We trained one neural network that takes as input the sketch and then predicts how the garment would look like in 3D. Another network would take the sketch as input and then predict the corresponding garment parameters. And then a third network can take the parameters as input and then predict the 3D draped shape of the garment. The main contribution of this work is to train these three networks jointly so that they actually share the same latent space, which we call the shared shape space. So now that we have this common latent space, it becomes very easy basically to go from one design space to the other just through the common latent space. So here is...
Can I ask a question?
Sure.
You could go back to this slide, just so we have an idea, what is the dimensionality of each one of these spaces there? I see 4 spaces here, I think.
Yes. So it really depends. For example, in terms of the garment parameters, we had different networks trained for different garment types because different garment types have different patterns. But I think we could say maybe the garment parameters are in the order of 10 to 20. In terms of body shape, we were using the simple body model, which has 10 PCA coefficients basically for the shape parameters. For the 3D draped garments, we did a similar PCA analysis. So instead of inferring the 3D vertex position of the meshes, we ran a PCA analysis on different draped 3D garments and we're using the PCA coefficients. I think we were using around 100 PCA coefficients. And input sketch is just represented as an image. I think it was either 256 by 256 or 512. I don't really remember the detail now.
And the shared space?
I have to check back, to be honest, maybe around 124, 1024. I might be mistaken though.
Networks going from down to from bottom of the page to the shared space. So that's actually increasing the number of parameters, right? So
yes,
maybe more
true.
like inverted
right.
cones we need there, right?
Yeah, that's true. That's
okay,
true.
Thanks.
That's true.
Thanks.
So yeah, this is a video recording of the system in action. So you start with this input sketch and then these are the predictions the network makes. So you see the garment pattern, the underlying 3D body, and then the draped garment. As I said, since we know the direct correspondence between the 3D and the 2D garment patterns, you can easily change the texture. Here you see the user basically going back and making a change to the sketch itself. So in this case, making the sleeves a little bit shorter and adding some fold lines and making the t-shirt a little bit wider. And once the edits are done, then the system updates the prediction. So just to make it easier for you to see, so this was the before and after, before and after. And then here is some examples of different edits. So basically, the user adds some additional fold lines to the bottom of the t-shirt, and then the draped garment is also updated accordingly. So before and after. And here are some examples where we found some reference images, acquired a sketch from them, and then give these as input to our network. Oh. So here you see the reference image, the sketch, and the draped 3D garments. So the colors of the garments were manually chosen by us so that they look more similar to the input, but you can pay attention to the geometric details. So as like many other learning-based algorithms where you learn this latent space, you can now start traversing the latent space. So here you see as you traverse the space, you also observe some smooth changes in how the 3D draped garment looks like. So in a way, you can think of the latent space as a fourth design space the designer can operate on in addition to the sketch, the parameters, and the 3D draped garment. So as I mentioned in the beginning, one common problem in garment design, both like in real world and also for computer games, is this problem of retargeting. So basically the idea is you want to design the same garment for different body shapes, but you want to preserve how it looks like. So in this case, for example, if you look at how the skirt drapes and the corresponding sketches, they have more or less similar fold lines. So the goal is to be able to take a garment design for one specific body shape and retarget it to different bodies. So one could say, okay, I have two different body shapes and I already have the garment design for one of them. If I use the same garment parameters and drape it on the new body shape, unfortunately it will oftentimes result in a 3D draped garment that is very, it's not very similar to what you started with. So we casted this as an optimization problem. So basically the goal is, given the new body shape, find a new point in our latent space so that if we drape this garment on the new body shape, it will look similar to our original garment. So there could be many ways to measure how different garments, how similar they are when they are draped. In our case, what we did was basically just do a non-photorealistic rendering so we can capture the fold lines and measure the similarity between those renderings. Since we train these networks, they basically act as like differentiable components. So you can just use some gradient descent type of optimization methods to find this point in your latent space. So here is an example. So starting from the same input sketch, basically we run this optimization to retarget to design this garment for the different body shapes, and so that they look similar when they are draped. Maybe I'll play the video once more. So yeah, this system was, I think, pretty cool and efficient, but there were some assumptions we made. The main assumption was we always designed the garment on a specific pose of the body. It was always an A pose, but of course, when you are designing a garment, you also want to look at how it drapes as the person changes their pose. So we did some initial experiments in the paper, but I think looking at how garments deform with body motion itself is a big problem on its own. So we have been recently looking into this problem, how to learn to simulate garments with different body motions. So here you see an example of simulating a garment in 2 different configurations. So let me stop the video here. So basically we simulate the same garment, one in a coarse setting. So you simulate a much lower resolution of the mesh, and then in a high resolution setting where you use the original garment. The high resolution setting is of course not only computationally much more expensive, but the physical simulation process is usually also hard to set up. You would need to adjust some parameters. And in this case, because of the complex interaction between the dress and this robe, at some point the simulation just blows up. So it's not robust, and you would need to maybe go back and then adjust the simulation settings again. So what we did in a recent work was, can we get the input from the coarse simulation, which is easier to generate computationally more efficient, and then use a machine learning to enhance it by adding these plausible wrinkles on top of it, so that you don't have to run the high resolution simulation anymore. And the input can be either a coarse simulation, or it could also be just a skinning based animation that you can enhance. So I'll briefly talk about this work. I won't go into details, but so here is the gist of it. So the input is a 3D garment mesh that is, as I said, obtained either by just some coarse simulation or just skinning based animation. And then we operate on the corresponding normal maps. So the actual input for us is the normal map obtained from this coarse simulation. And we want to enhance this normal map by adding some plausible details on top of it. The main motivation, the main contribution of this work is actually cast this problem of adding details as a style transfer problem. As you may know, style transfer is recently very well researched, and there has been a lot of progress. So let's first see why this problem can be a style transfer problem. So here you see the normal maps of a garment obtained with coarse simulation and high-res simulation. And then in this plot, you see the 2D feature embeddings of these two normal maps. So we just use some image classification network like VGG to obtain some features and then plot them in 2D. As you can see, the statistics of the coarse and high-res simulation is very different. So our motivation was, can we now take this coarse normal map as input and then make use of a data set where we have simulated this garment and then transfer the feature statistics from this data set to the coarse garment. And here is our result. And here is a plot, again, a map plotting the same feature statistics. And as you can see now, the features are much closer to what we want, the high-res simulation. So yeah, the basic idea was, okay, the goal is to enhance these normal maps and let's cast this as a style transfer. In our case, style means basically the details of a garment with the same material properties. And when it's simulated under different motions, we can transfer those detailed statistics to a new input. So yeah, with this motivation, basically we designed this detail enhancement network, which is very similar to a style transfer network. The two main things is, of course, we want to make this network generalize across different garment types. Different garment types might have different normal map topologies because they will have different 2D patterns. So in order to generalize across the different garments, instead of looking at the whole normal map, we actually operated on local patches in the normal map. So the network does not see whether this patch is cropped from a skirt or a garment or a dress or a pants. It just operates locally. And the other thing is, of course, how the garment simulates is very related to the material properties. And in our case, we actually see the different materials as different styles in style transfer. So in some recent universal style transfer methods, one common way is to use these adaptive instance normalization techniques. So basically, you train your network and based on the different styles you want to transfer, you try to adapt the parameters of your network by some simple scaling and shifting. So we use the same trick. So we have a network trained, and based on the different material types we have, we add this adaptive instance normalization layer to adjust the parameters of the network so we can generalize across different material types. So yeah, basically the gist of it was really look at this problem as a style transfer task. And here are some results. So basically you will see results with different garment types made from different materials. You'll see the coarse simulation on the left and our result on the right. Maybe I'll stop at some zoomed point. So yeah, basically, if you look at these zoomed versions, the system just adds more detail so that the results look more vivid. So yeah, this is one recent work we did, and I'm also interested in like looking at this area of using neural networks to approximate the physical simulation processes. Of course, garments is one special case, but I think one can also look at this general problem. So here is like a very short clip from some work that is currently under review. So the goal here is to use a similar approach, to use neural networks to approximate soft tissue dynamics. So basically starting from an input 3D mesh, which is animated by just skinning-based animation, the goal is to add these secondary dynamic effects. So what you see in this image is at the bottom, you see the same mesh with some color coding. So the darker the red is, it means we want the the corresponding region in the mesh to be more, let's say, jiggly. So we want to simulate more secondary dynamics. And if the color is lighter red, we want that region to be stiff. So we trained this machine learning method basically that takes this input and tries to add the secondary motion on top of it. And yeah, this is basically how the results look like. So yeah, with that, I now want to change gears a bit. So in this first part of the talk, we looked at garments, and for the garments, we assumed we have these good template models. Like we assumed for a, let's say, a shirt, we know how the 2D garment patterns would be. For a skirt, it's gonna be a different set of garment patterns. So it was really a model-based approach. But of course, it's not easy to come up with these template models in the general case. So now I would like to introduce you to another recent work where we looked at the 3D reconstruction task from a more general perspective. Using implicit functions specifically. So what are implicit functions? So implicit functions are commonly used in computer graphics as a 3D representation. So basically, given a 3D object, you can reconstruct the surface of the object by basically dividing the space into two. For every point in the space, you can represent the distance of the point to the surface, and this distance can be signed positive if it is outside the surface and negative if it is inside. The main advantage of the implicit functions are, of course, they are model free, so they are more suitable to represent like different topologies, different objects. And in theory, they also provide infinite resolution since you can take as many samples as you like. So they're good for capturing details. And it turns out that they are also actually very suitable for machine learning since they are continuous. Neural networks are doing a good job in terms of predicting them. So that's why we have seen a lot of work in this space recently. So a common approach has been, can we train a network mostly in the form of multi-layer perceptrons that would take a point in 3D space, X, Y, Z, extract some point features from it, and then attach another latent code Z, and then give this information to a decoder that will predict the corresponding sign distance of this particular point. So if we want to apply this same method to the task of single view 3D reconstruction, I guess the naive implementation could be, now I have my point and the features extracted from this point. And in terms of a random latent code Z, I can now extract some features from my image and then give these features, the image features and the point features to a decoder and then predict the sign distance of this point. If you do this for many sampled points, you can then run some 3D reconstruction algorithm like marching cubes to obtain the final 3D shape. So this is how this method would work for this particular image. It looks reasonable, but it also lacks a lot of details, especially on the back of the chair. So main reason for this is for any point that you sample, like for a point that is maybe on the seat of the chair or a point that is on the back of the chair, we are always making use of the same global features that were extracted from the input image. So this is not sufficient to capture the details. So what we did in this work was basically to replace this part. So if I can estimate the viewpoint from the given image, for any 3D point I sample, I can now project this point to my image space. So in addition to the global features I already have, I can now start extracting some additional local features around the point where, around the projected 2D point. So now I'm gonna make again a sign distance prediction, but I have my global features, point features, and in addition the local features to capture more details. Of course, one option is to provide all those features to a single decoder. What we did in this work was actually have two different decoders. So one decoder is similar to what I described in the beginning. It takes the point features together with some global image features to predict the sign distance field. And then we have another decoder that takes the point features and the local features and makes another sign distance prediction. And then we concatenate the two. So you can think about this as the global branch is responsible for basically learning the overall shape of the object, and the local branch is adding the details on top of it. So basically it's learning the residual. And with this method, now you are able to get much more details compared to just using the global image features. So here are some additional examples. So by adding this local prediction branch, basically we can capture these different topologies. You see like the circular holes are captured much better than just doing using global image features. So one good thing about these type of networks is it's also very suitable to increase the number of views. So let's say you started with some single image, but you can add more images to your network. So when you extract your image features, basically you can just do some average pooling or max pooling to combine the features coming from the different images. And obviously, as you add more images, the quality of the reconstructions will increase. So it's also nice that the network is flexible enough to get more inputs. So yeah, this was another work that we did in the context of more general 3D reconstruction. So now I would like to speculate a little bit on what we can do next. But in order to do that, I want to first revisit some of the questions we casted in the beginning. So the first question was, what type of 3D representations are usable for different applications? So for the two applications I showed today, they were using different representations. For the garment work, as I said, we made the assumption that for a particular garment type, we know the corresponding patterns themselves. So it was really a model-based approach. We have these templates that come with some parameters. By changing these parameters, you can generate different instances. I think the main advantage of using these template-based approaches are, of course, they are easy to control. The parameters themselves already give you a good space where you can do these edits. And usually these parameters also have some semantic meanings. For example, you might have one parameter that corresponds to the length of the sleeve. So it's very easy to cast editing with these semantic parameters. Another big advantage is if you now generate different instances of the same template, you also get correspondence for free across these instances. On the downside, they are topology dependent. So for example, for different garment types, you would need to design different templates. So for different topologies, you would also need to design different templates. And also they do capture the overall shape well, but they may not always be suitable if you want to capture the details. In the second work, we use implicit representations, which can actually address some of the limitations that I mentioned before. So they are more general, so they can adapt to different topologies, and they are also more suitable for capturing the details. And as I said, it turns out they're also very suitable for neural networks. That's why we are seeing a lot of excitement and a lot of advances In our work, for example, we were predicting just the sign distance of a given point. There has been a lot of work that also predict the RGB colors, so you can actually get texture 3D models. You can predict neural features and then use some neural rendering methods to, for example, synthesize novel viewpoints. And as you, most of you may know, you can also predict radiance fields, which has gained a lot of popularity. These are all advantages of the implicit representations. On the downside, though, they are not as easy to interpret as explicit template models. So if you want to do some editing now, you would need to edit these implicit features that you have learned. So it may not be always trivial to map them to some semantic edits. So moving forward, I see that perhaps a hybrid representation between model-based approaches and implicit representations might be very useful for certain applications. We have actually started seeing some examples of this. So this is some recent work from capturing human body shapes together with the garments. As I said in the beginning, for faces and human bodies, we usually have good 3D deformable templates. So it's a very nice representation to represent the underlying body shape. And then on top of it, one can use implicit functions to represent some garment details. So in some ongoing work, we are also looking at these hybrid representations for modeling human scene interactions. So again, for humans, we can use model-based representations, but for the scenes, since there might be a lot of variation, implicit functions might be a good choice. And having implicit functions also helps to model basically some interaction, for example, the contact between human and the scene. So yeah, moving forward, I think there is more work to do here in terms of using these hybrid representations and leverage the best of both worlds. The second question we had was what type of 3D priors can we explore? So if your 3D representation is a model-based representation, a natural prior is actually some statistical priors that you learn on your model parameters. So I think one interesting future direction is how can we make use of this fact to add some 3D priors to implicit representations. For example, can we train, for example, some neural network that makes use of 3D face models? We already know what a typical 3D face would look like, so we can inject this prior to our implicit network, but we know a deformable model may not be able to capture person-specific details. So we could then leverage implicit functions to capture like person-specific identity details or specific expression details. So I think especially in the context of human faces and human bodies, bringing in the information from 3D deformable models to the implicit networks seems like a good next step to explore. And finally, the last question was how can we see through occlusions and make use of basically extend the limited observations we have. In the works that I showed, we did not have any explicit way of handling this. We just expected the network to learn to reason about occlusions just from data. I think in some specific problems, we actually have very interesting explicit cues that we can utilize. So for example, look at this video of multiple people doing more or less the similar dance. It's not perfectly synchronized, but if you look at this person in the back, even though we did not observe what she was doing for most of the time, we all have a very good idea of what her motion was because we already saw the people in the front doing a very similar motion. So I think it's interesting to look at those cues like there are lots of videos of multiple people doing similar dances or similar sports. So injecting those additional priors for human motion performance capture seems like an interesting problem to look at. Similarly, if you look at this particular image, even if we don't see the lower body of the person, we can all hallucinate how she is most likely sitting, because we know what the space of plausible sitting motions are. So leveraging those common human scene interactions to improve human pose estimation, but also to improve the 3D scene reconstruction, I think is also another interesting problem to look at. So yeah, those are some problems that I have in mind to explore more in the future. And before I conclude, I'll just do maybe a 5-minute advertisement. So as I could said, I've been at Adobe Research for the past 6 years. Just for you to get more information, so Adobe Research has offices in different locations, mostly in the US, but we also have a recent office in London and one in India. I'm actually myself in the transition phase of transitioning from the San Jose to the London office. And we do a lot of research in like graphics, vision, machine learning, and publish at many conferences. And many of these publications are actually as a result of internship projects and academic collaborations. Actually, ICUD, Deniz Hoca, and ICUD, we have an ongoing collaboration currently. So basically, Adobe provides a very flexible environment for us to work with academia. So yeah, if you are interested in learning more of like internship opportunities, full-time opportunities, and also academic collaborations, I would be happy to chat more later. And yeah, that's all. Thank you. I'm happy to answer any questions.
Thank you, Duygu. So, any questions from the audience?
Well, if there are none, I will ask one. Excellent presentation, by the way. I don't know how many papers jammed together, but a lot of work. Very interesting stuff. I had a question about the data you worked with, the sketches you worked with, as well as the garment templates. Were they, so I assume the templates were from real databases or of real clothing. Yes. How about the sketches? Were they designer created? How did you curate these sketches?
Yeah, that's a good question. So basically, we started with some garment patterns that you can actually purchase online. There are these softwares like Marvelous Designer that sells these patterns. So we started with those, and then we generated many variations of it by adjusting the parameters. And then you have the 3D garment, and we just rendered them with non-photorealistic rendering to generate our sketches. It's a easier method to get large-scale data. The downside is maybe the statistics of the sketches does not really match what a user would draw in reality. So yeah, that's an interesting question, but yeah, otherwise it would have been very difficult to get such a large-scale data set.
Okay, following up on that, do you have an idea of what kinds of features people put on paper when they do sketch? You had contours and you also called these draped lines, right?
Right. So that was what we mostly focused on, like the overall contour and then some adding these wrinkle lines. There are some other works that look at this in a more systematic way, like maybe adding some pleats to the sketches, different lines for that. In our work, it was mostly the two that you mentioned.
All right, thank you.
And related to this, Duygu, first, thank you. Actually, it was really a nice presentation. I assume actually, as Metin Hoca pointed, you collected, and you should have collected such a huge data set, and you learned a joint representation of different spaces. I bet there should be also a mapping from, I don't know, from the parameters to the sketch space. Is it of your interest, or is it basically can it deliver some good news actually to see how changing a certain parameter affects the sketch and affects the final design eventually?
Yeah, that's a good point. So we did not look at in particular like going from parameters to sketch, but for the retargeting work, we were actually measuring the similarity in terms of the corresponding resulting sketches. So we had another network that would take the 3D draped garment and automatically generate the sketch, kind of do like a differentiable sketching of the 3D draped garment. So it would be interesting to see how that would perform if you go from parameters directly.
I have, again, this can be also like a follow-up question. So do you have this shared latent space between these different modalities? So especially on this garment design problem, does it make sense to have not a single latent space, but build that like a hierarchical manner? Because like there are these different clothes that, like you said, you trained these different models for each type. Maybe you can just build a large big model.
Yeah, that's a very good point. I think even for the same type of cloth, so our system currently just models the overall shape, but think about a shirt. It might have a little pocket, and the way you sketch that pocket, I think, would be very different than how you sketch the overall shape of the shirt. So yeah, if you have this like hierarchical approach, it might help to model these like small details like the pockets, belts, other like accessories on top of the cloth much better.
Or maybe like the parts, like the body or the arms, they can share.
That could be another way of looking into it.
I actually have a quick question. Thanks again, Duygu, for the very nice presentation. About the simulations where you go from like coarse to fine. Is there a, let's say, elaborate way to add some physical constraints as well, some boundary conditions? Because when I happen to observe these situations, usually going from coarse to fine requires a lot of additional simulation time. But actually that is even so for the cases when you need to embed another physical constraint. I don't know if you happen to try anything like that.
Yeah, that's a very good point. We haven't looked at it ourselves. So yeah, for example, it might happen that you have a fine simulation, but in the end, you might observe some, let's say, self-intersections between the cloth and the garment. There are some other methods that look into this, like how to resolve those collisions and so on. We haven't looked at it. I think it's still a challenging research direction how to include that.
And alternatively, like if you want to embed like a physical force, like wind force that you want to change the environment, did you have any work around that direction?
Not explicit forces, but for the this secondary dynamic project. So basically what we did here was our neural network was somehow following the physical simulation process. So we had, let's say, one MLP that would predict like the inertia of a vortex, and another neural network that would try to represent forces between two vertices, internal forces between two vertices, and then combine them to predict the final displacement. But we haven't looked into adding an external force. I think that's also an interesting thing to look at.
Thanks again.
So any other questions, especially from our students? Okay, then I think we can finish here. Thank you again, Duygu. This was really very nice and very interesting talk.
Yeah, thank you for the invitation.
If possible, I'd like to have a question.
Yeah, sure. Go.
Okay, so like it was mentioned in the first, when it comes to the garment, that one downside of it couldn't catch the details of the garment.
Mm-hmm.
But it was mentioned in the second that the second, not presentation, but in the second model that you presented, it can easily catch the details. Why it was not used also in the first one, so that we can catch the detail of the garment?
Maybe I think I should not use detail in both contexts. In the first context, by detail, what I meant was more like geometric features, like adding a pocket on top of a t-shirt. In the second example, with detail, I was referring more to like wrinkles, additional wrinkles. So sorry for that confusion. I was really meaning two different things.
Okay, thank you. Thank you so much.
By the way, do you have the CGraph 2021 paper already available anywhere?
The Eurographics, you mean?
Yes.
Yeah, I think we have it on archive.
Okay.
You mean this one?
Yes, this one.
Yeah, this is on archive.
Okay, thank you.
Tekrar